Lesson 19, non-ohmic devices and components. So today what we're going to do is we're going to do a couple of little things. We will learn about non-ohmic devices and exponential graphs. And that's going to be the aim of today. So yeah, we'll see how we go. What did we do last time? I just already talked about it before, but just so that we have a record. Last couple of lessons we've been powering through circuits. We would start off with what a series circuit is, where the current's the same all the way through. The voltage, you sum the voltage and you sum the voltage and you sum the resistance. But with a parallel circuit, instead of adding together all the resistors, you add over 1 over all the resistors, and therefore, and that will give you R total. And also, each path through the circuit has a voltage drop equal to the cell. We went through some basic practice one, where we added them. Then what we did was we went through 6 examples. First example, series circuit, 2 resistors, the same amount. Second example, series circuit, 2 resistors, different amount. Third example, 2 resistors, different amount, but instead of giving you guys both resistors, I gave you one of them and not the other one. You had to work it out. Then we started working on parallel circuits. Remember, parallel circuits, the idea is that 6 volts gets dropped here and 6 volts gets dropped there. That's how we would work that out. And then, of course, the rest of that is to calculate. The big one is the current, I being for current. What is the current through this branch? What is the current through this branch? What is the current at the end when you add these 2 branches together? What is the final current added together? Then we did some advanced parallel circuits. These are circuits where the resistance was different. We said because of that whole, because we said, like at the beginning, electrons preferred path of least resistance, there will be more current going up than down. And then the last one, we had to backtrack. We know there was 10 amps going through here, and then we figured out there's 4 amps going down here. What must be the amount going up? What must this amount be? And we had to work that out, and that was 6 amps. And then once we did that, we could then work out what this resistance was. I sort of showed you this, but I said, listen, it's the same sort of idea, but we're not going to talk about this because it's a bit too advanced. But today what we're going to talk about is we're going to talk about non-ohmic devices. And how do we get to a non-ohmic device? What does non-ohmic device mean? We know what is an ohmic device, and so how does it compare? And we're also going to look at this new idea here, exponential graphs. Now, some of you guys that are in advanced maths might have already had a chance to see what an exponential graph is. But for those of you that have never seen them before, well, get yourself ready, because we're going to look at what they look like for the first time. Before we do that, I wanted to do a quick little practice. We're going to see if we can work out how to solve this question together. Can I get someone? Firstly, I'm going to check on chat, but also if you want to speak out loud, you can. Can I get someone to start off? Is this a parallel circuit or a is this a parallel circuit or is this a series circuit? Parallel. Beautiful. This is technically a parallel circuit, so that means we're going to use our parallel rules. Okay, next question for the Zoom chat, which I'm going to keep open now. Can someone tell me what is the voltage drop over the top resistor? We're going to call this one A. What is the voltage drop over A? John says 6 volts. John is unfortunately incorrect. It's not 6 volts.
8, Mr. 8.
It's not 8. Aaron is correct. It is 12 volts. 12 volts gets dropped over the top one, and 12 volts gets dropped over the bottom one. They are the same amount of voltage. Okay? The reason is because if I follow the current around, 12 of it has to get dropped over this resistor. Otherwise, it'd go back with, you know, still some voltage left over. So when you do a question which is parallel, essentially 12 volts gets dropped here, 12 volts gets dropped here, and matches the battery. So let's do this together. V, A, V, B, V, T, 12 volts, 12 volts, 12 volts. Okay. What is the resistance in A? What is the resistor for A? So do we know what the resistor for A is? Someone in chat?
Eight.
It is 8. It is
Oh,
not.
did I get it right?
It's not 8. We don't know what it is.
Oh.
I just jumped to the answer. It's not 8 because we don't know what it is. With RB though, what's RB? What's the resistance through B? Can you tell me what the resistance through B is? 30. We do know the resistance through B. We don't know the total resistance because we don't know RA. We can't possibly work out the total resistance. Okay. But what about current? Do we know the current through A? No. Thank you, Aaron. I appreciate that. Do we know the current through B? We still don't know the current through B. What about the current? What about the total current? What is the total current? Do we know what the total current is? We do know what the total current is saying. What is the total current then? It's clear. 2 amps. Thank you. The total current is 2 amps. Now, that's all the information we can take straight from the picture. So now what we need to do is we need to rely on our V equals IR formula because we can use that here. V equals IR, which means that V divided by R is going to give us I. Specifically, VB divided by RB is going to give you IB. So VB, which is 12 divided by 30 is going to give you 12 divided by 30 is going to give you, what is that? 0.4. Is that what you guys are saying? Aaron said, okay, Aaron's jumped ahead a little bit further than I wanted to, but that's okay. 0.4 amps. Now, if you know that it's got 2 amps going in, right? We know going down is 0.4. How much is going to have going up? 1.6. Anyone else agree with Aaron? Has Aaron got it right?
Yes.
Aaron's got it right. 1.6 amps is going up because remember we have to make sure that those amps are conserved, right? So therefore this is going to be 1.6 amps. If I know that's 1.6 amps, then I can immediately then do the same thing that I did here. R is going to be RA is going to be VA divided by IA. It's going to be, well, we know 12 volts is dropped over it. We know it's 1.6. 12 divided by 1.6 is 7.5. 7.5 amps, ohms. And we can also use that same method to get RT. RT is going to be VT divided by IT. It's going to be 12 divided by 2, which is going to give you 6 ohms in total. Now, I was talking about this to my physics students. I found it really weird that the total resistance is less than each individual resistor. And that's just because when there are more paths for the current to travel down, that means there's going to be less resistance overall. Even if they've got to travel down each individual resistor, overall it's just going to be easier for the current to go through. Kind of like if you've got a piece of material and you want to put water through it, it's easier to get that water through with lots of tiny holes than just one tiny hole, even if the hole is tiny. Bit of a bad metaphor, sorry. You know, I give that metaphor 2 stars out of 5. Let's keep going. So what we're going to talk about today is we're going to talk about measuring circuits first. Before we talk about the different types of circuits, we're going to do a different ohmic versus non-ohmic. We're going to talk about how do we measure these circuits. We've spent a lot of time talking about how we can calculate circuits using V equals IR. But what about measuring it? For example, in this question here, when I said it's 2 amps, how do we measure that in a circuit? Well, how you measure that in a circuit is you use 2 devices. You use a voltmeter in a circuit to measure voltage. And an ammeter is designed to measure current. Notice how volts and ammeters are named after the units that they measure. Current's measured in amps, voltmeter measures volts. Okay, is that clear with everyone?
Yes.
No, it doesn't measure meters. Aaron. Okay. Okay. So yeah. So the idea is that they will measure. You don't. I'm not really. They really good. So okay. Saying. So a voltmeter. We're going to go through in a bit more detail anyway. So don't stress. But we're going to start off by talking about the ammeter. Okay. What is an ammeter or an ammeter? How does it work? What does it measure? Okay, we're going to start with that. So an ammeter is connected in series in the circuit. Okay, and what it does is and this is the symbol, and it has a very low resistance. And because there's a very low resistance, what it does is it actually, and so it doesn't affect the circuit because it's in series. What it does, and as the main basic idea is, as charge travels through an ammeter, it will change how much, it'll change what it measures. If a lot of charge goes through an ammeter, then it will measure a high current. When only a little charge goes through an ammeter, it'll measure a low current. And how it usually does it is with, in the old days, we used to do with a needle. It would create a magnetic pull which would push that needle whether to a very, very high current or it might push it to a very, very low current. But the idea is it changes the current. Okay, so that's our first thing. An ammeter, symbol A, has a very low resistance and it doesn't want to affect the circuit too much. Now, how do you set these up? An ammeter in a circuit is always connected in series. So if you want to measure, this will measure IT. This will measure the total current of the circuit. Because all of the current must pass through here before it gets to the battery. Or as it comes, sorry, drawn the wrong way. As it leaves the battery, all of the current goes through here. Same with this one. As it leaves the battery, all of the current goes through here. Now, if I put an ammeter, hold on a second. If I put an ammeter here, right, then what that would do is if I put an ammeter here, what that would do is it would measure the current through this specific part of the circuit. If I put an ammeter here, then it would measure the current through this particular part of the circuit. So that's how it works. Let's see. Okay, so let's now look at one more thing. The reason that I said this is in series is because it has to go through one and then the next one. There's only one path. Even though this is a parallel circuit, it still has to go through one path. I'm going to show you now a voltmeter. Now you look at this. This is an example of a voltmeter. It's pretty much the same thing. It actually is the same device, just on different settings. A voltmeter is connected in parallel to a circuit, and it has a high resistance. So because it has a high resistance, it's very difficult for the for the electrons the charge to drop voltage of them. Well, not much current will go through it. You don't want much current going through a voltmeter because it's measuring how much voltage is dropped over it. So you want just a tiny bit to be dropped over there. It has to be connected in parallel. It has a symbol V, and it will also usually work with either a digital device or it will work as some kind of detector sensor thing. And as it gets more and more voltage, it will turn the dial more and more to the right. Okay. Now, how do you set these guys up? A voltmeter is connected in parallel. What that means is, so if I set this up here, like this example here on the left, as the electrons go through, so as charge goes through here, it's going to drop something. Maybe say it drops 3 volts. Some charge is going to go up through here. And we know already, because of our understanding of parallel circuits, that if it drops 3 volts down the bottom, at the top, it has to drop 3 volts at the bottom. So that's how we can use this to measure the voltage drop over a particular light bulb or a particular resistor, because they have to drop the same amount. The trick is, though, is that only a tiny bit of voltage will go, tiny bit of current will go through there. We want most of the current to go through this upper channel, because we don't want to interrupt the circuit. We just want a little bit of current to go down there, just so we can measure the voltage. Same situation in this example here. If I've got resistor A and resistor B, then this resistor will measure the tiny bit of voltage going through this resistor, whereas the majority of it will go through this one. But if this drops 5 volts, then this one will also drop 5 volts. It's really important that, you know, even if it's always hooked up around one of these light bulbs. I find that these pictures are also really misleading. The reason that I don't like these pictures is that it's really obvious to us that this is the situation going on, because it's really obvious to us this is the situation going on because of the picture. But the problem I hate with this is in real life. When I ask students to wire up these circuits with a resistor, they will usually, with a resistor and a voltmeter, will usually accidentally put the voltmeter in series instead of in parallel. And then they'll be like, why isn't it working? And it's like, well, because you've done this, this, and this. So it's all about you've got to make sure you know how to go from the real world example to a picture example. Now, if I got, let's see, what else? Next up, is reading an amp meter. I want you guys to have a quick look at this. And this is going to be a bit of a weird question, but I want you to tell me, what do you guys think the current is through this amp meter? What is the current through this section here? Anyone? I'm waiting for someone to tell me what is the current through that section. 6?
No, it's 8, mister.
8?
Yeah.
It's not 8 and it's not 6. It's not 11 either. 10. Close? No, but not quite. It is max though. It's not 1, also close. Okay, here's the trick with this question here. It is, because it looks like it's definitely the max. So it's either 1, 5, or 10. The question is which one of those three things is it? And the trick is to look at this bottom part. These wires are actually plugged into 5. So that means that this scale is actually measuring from 0 to 5. So we would say the voltage on this amp meter is the current on this amp meter is 5 amps. Now, the reason I know that it's 5 amps is what we do is in an amp meter is, because these are the old-fashioned ones, and even on the new ones we do this, we need to have a scale. So for example, the first scale is from 0 to 1, okay? So if you're measuring something that's got like less than an amp, you want to make sure that it's accurate. So you want to make sure that you know exactly where it is. So you would use an amp meter that measures from 0 to 1. But let's just say now, instead of using that, you're using a really big circuit that's got a lot of current. You might instead choose to use 0 to 10, because maybe you're dropping 6 volts, 6 amps, or 10 amps, or something like that. Now here's something that's interesting. How could you ensure that this is accurate? I always like showing students this. This is a bit of a numeracy thing. Now, it might say, even though I said the answer is 5 amps, I could actually then turn around and say, are you sure? Because think about it, right? If it was something like, I don't know, let's say it was 8 amps, right? If it was 8 amps, right? Even if it was 8 amps in the circuit, and you were measuring between 0 and 5, it would max out. And that's actually the right use of the word max out. You would max out at 5 amps. So even though it's 8 amps, it could max out at 5. So therefore, if it was maxed out at 5, you would then say, well, you can't tell if this is actually 5 amps or 8 amps or 10 amps or 12 amps. You can't really actually 100% know. The best way to check is if you move this wire over to the 10 amps and then the needle moved down to 5, then you would be 100% sure that that was actually a 5 amp circuit or 5 amp reading. So you're just going to be this, I guess, get students, I'm trying to get you guys familiar with the idea of maxing out something. If you've got a scale at a, if you're trying to buy some meat and you've got a scale that can only measure up to 2 kilograms, and you put 5 kilograms of meat on that scale, it's going to measure 2 kilograms because it's going to get maxed out. If you want to measure how tall someone is and you only have a meter ruler, you're going to measure them to be a meter tall because that's as maximum as high as you can measure. So that's why there are multiple dials on this, so that we can make sure that you don't max out the ammeter. Now, the last thing I like to always talk to students about is this common mistake. It's a bit of a challenge here, but why must amp meters be connected in series but voltmeters are connected in parallel? We already sort of talked about this, but I wanted to talk about one of the problems that happens when you hook these up wrong. When you have a voltmeter, if you have a voltmeter and you hook that up, let's just say you hook that up in series, okay? This isn't a big deal, but if you have a voltmeter, let's just say it's hooked up to a light bulb, you know? And I've seen students do this a lot. They'll hook a light bulb up to a voltmeter. What will happen is that they'll see their light bulb will be dark. And they'll say, "Why, sir? Why is my light bulb dark? I just want to measure the voltage." And I say to them, "Well, what do you know about voltmeters? Voltmeters, it has a high resistance. So when you hook this up, this is probably dropping, let's say this drops 2 ohms, right? This one is going to drop like maybe 5,000 ohms. Now we'll make it 50,000, make it something stupidly high. 50,000 ohms. So this guy, if this is a 10 volt battery, this guy's going to drop 9.99 volts. And this guy's only going to use up 0.001 volt. So therefore, because it's going to use up no voltage, this is going to be pretty much black. The light bulb is not going to switch on. And I've had students say that to me in the past. They're like, "Sir, why doesn't my light bulb switch on?" Because all of the voltage is getting dropped over the voltmeter. The correct way to hook up this circuit would be instead to put the voltmeter around the light bulb like this, and then that would make it work. The second problem that I see students make mistakes on is with the parallel circuit, with the an amp meter. So let's say I've got this situation here. Oh my God, I hate it when students make this mistake. So they are common mistakes, don't worry. This one here, this one's a little bit worse though. Now, in comparison, an amp meter doesn't actually drop. An amp meter is connected to is a low resistance. It's supposed to be connected in series. So because there's a low resistance, right, you actually have this problem happening. What happens is, in a low resistance, you're going to have the current is going to go through here, and it's going to get to this point where it's going to have a choice. Do I want to go through the do I want to go up and through this amp meter that's maybe got 0.01 ohms? It's really easy for me to go through. Or do I want to go through this 10 ohm light bulb? Most of it, if not all of it's going to go up through the amp meter. The amp meter is going to then shoot through the roof. And here's the problem, right? That current is then going to go back to the battery. There is now no more places for that current to drop its voltage. So it's going to drop its voltage here. what you've done is you've actually created a short circuit. You've created a path of very, very, very low resistance. Effectively, what you've done is this to the circuit. Because you've done that to the circuit, all of the voltage is going to get dropped through the amp meter. What happens here is that I've had a couple of students come up to me very quickly during the lesson and say, "Sir, my amp meter is not working." And then I look at it, I try it out, and it turns out that the students have killed their amp meter. And yeah, you can't kill a voltmeter by hooking it up in series. Because if you hook a voltmeter up in series, then it's like, oh, whatever, it doesn't work. But you can kill an amp meter by hooking it up in parallel. And so I'll get every so often, a couple of classes, I'll get a dead amp meter. This is why we only let students use variable voltmeters that go between 0 and 12 volts. Because if we gave you anything more, it would be, we would have dead amp meters all over the joint. So that's why you can't hook an amp meter up in parallel, and you shouldn't hook a voltmeter up in series. Now, I'm going to keep going. I'm going to talk about this. Oh, by the way, I want to point out, I know this is sort of going to make me a little bit sad, but normally what I would do at this point here would be, this would be a short lesson. So normally this would be the start of period 6. And then I'd say, right, guys, I want you guys to practice making a series circuit and a parallel circuit. And I love this lesson because it gets students to, I've just said, don't hook up the amp meter in parallel. And usually what happens is students don't make that silly mistake. So I'm usually like, thank God. But I usually get students to make circuits. And I really find it interesting as students try to understand, how does like this circuit, you know, I want to do this, and then I'm going to maybe get another alligator clip and attach it there. And they're going to get another one, and then they usually go like that. And then they try to go like that. And they're trying to make a circuit. And I'm like trying to get them to like, have you made a series circuit or a parallel circuit? How do you know? Are you sure that it works? And they usually make a couple of mistakes, because it's very easy to look at this picture here. But it's sometimes harder to then go and make that actual physical circuit in the real world, because wires don't line up on straight lines. This one's actually interesting because you can see here that this line goes to make this point here. But then this student has then hooked this wire directly to there instead. And that still is a, that's technically still a parallel circuit, but it doesn't look as neat, and you might be confused by that. But still, it's parallel circuit. Current can either go through this route, or it can go through this route. So it's still a parallel circuit. Of course, because we're at home, and I don't want to encourage you guys to rip apart your closest electronic device, we can't do this. We can't do these circuits in like at the moment in isolation. So what we're going to do instead is we're going to keep moving forward, and then hopefully if we do go back in the next 3 or 4 weeks, then we can come back and we can actually make our own circuits and basically apply what we've learned. So here's my question. I'm going to let you guys sit with this question for a second while I quickly go grab a glass of water. The question I have for you guys is this: why use a voltmeter and an ammeter when we can then calculate everything using Ohm's law? We have a perfectly good way of working out the theoretical things. Why would we use an amp meter for? Have a think about that. Be right back. Okay, let's have a look. See what you guys thought. First person said time efficient speed to be exact, because theory doesn't always link up with results. Hey, Angus, I'm in love with Jess. Okay, cool, excellent. Now, why use a voltmeter and an ammeter? Yes, speed is correct. It is very quick to be able to go beep beep instead of like it's this many amps rather than trying to look it up. But, and it's really good, Jason, to be Reese, to be exact, you know, sometimes to double check your results. But what I like is Jason actually hit the nail on the head, because what you will have is circuits don't always follow the rules. What that means is that sometimes it's great to know Ohm's law. It's great to know V equals IR, but that doesn't work if it doesn't follow the rules. And so sometimes you really need to know. Why I learn it, because most of the time it is right. There's only some exception when it's wrong, but it isn't really important to understand what happens when it is wrong. And so circuits don't always follow the rules, so sometimes it's a good idea to measure a circuit's current. So what are these things that don't follow the rules? A non-ohmic device is a device that doesn't follow Ohm's law. The voltage drops and current and current does not scale linearly. So this is one of those situations where, you know, one thing happens, the other thing. This is one of those situations where if it might not necessarily work both ways. It might not necessarily work that V equals IR. By the way, guys, I've turned off chat for a little bit because I think you guys are getting a little bit too distracted by what's going on there. Just so that you know. So what does it mean to say that? What does it mean to say that a device is non-ohmic? What does that mean? Voltage and current, the voltage drops and current does not scale linearly. What does that mean? What do you mean scale linearly? I'm going to show you what that means here. And we're going to look at two examples of non-ohmic devices. And we're going to start off that journey by looking at Ohm's law and ohmic resistors. Okay. Now, Ohm's law is pretty much this idea, V equals IR. So these are the things that do work. These are things that follow the system. So this is an ohmic resistor, so it's just a regular old resistor, nothing special here. What happens if you increase the voltage? Well, what happens, let's say instead of using a 2-volt battery, we use a 4-volt battery, or a 6-volt battery, or 8-volt battery, or a 12-volt battery. What happens? Well, as you increase the voltage, what you're doing is you're giving the electrons more energy. They have more fuel. They're able to move faster. So therefore, what you end up with is at 2 volts, you might only get 1 milliamp. Okay. At 4 volts, you've doubled the amount of voltage it's got. So because you've doubled the amount of voltage, guess what? You double the amount of current that can go through. Then at 8 volts, that's double 4 volts again. So you double the voltage, guess what? You double the current. The current goes from 2 amps to 4 milliamps. We're increasing the current. And as you keep going up, you will increase the current. Now, this is what we would call a linear line. As the voltage goes up, the current goes up. That makes sense. More voltage means more energy. More energy means it can move faster. The resistance of this circuit is actually 2000 ohms. You can actually work out the resistance of this by just taking any voltage. Remember, resistance equals voltage divided by current. So if you take any of these examples, you can go, for example, 4 volts divided by 0.002 milliamps. It's going to be 2000 ohms. Here's another way, though, that we could actually work this out. We could actually look at the graph itself. This is a bit of an advanced idea here, so if you don't understand this, it's okay. The gradient of this graph, right? M equals rise over run. And the gradient of this graph is the rise is current over the voltage, the run. So that means that if I look at current divided by voltage, current, if R equals V over I, then that means if I take 1 on R, is going to be I over V. So that means that the gradient is actually equal to 1 on R, 1 over the resistance. If you don't understand what that is, that's okay. The main idea here is that it's a linear line, straight line. I'm going to unmute the chat now because I want to be able to see what you guys come up with ideas. But yeah, let's keep moving forward. So back to the idea here. Ohmic resistors have a linear relationship. As the voltage gets more, as you give more energy to the current moves faster. You give more energy to the electrons move faster. If the resistance stays the same, nothing happens. So that's what Ohmic law is. That's what Ohm's law is. That's what an ohmic resistor. What about these rule breakers? What do they do? Well, a rule breaker, a non-ohmic resistor, is going to act a little bit differently. We're going to use the same axes here. 2, 4, 6, 8, 10, 12 volts. And we're going to use, I think what we're going to do is to make sure that we can fit everything in, is we're going to go up by 200 milliamps. So we're going to go 0.2, 0.4, 0.6, 0.8, 1, 1.2, and these are all amps. So how does a non-ohmic resistor work? Okay, well, 2 volts, we've got 1 milliamp. Okay, so 1 milliamp, that's 200 amps is here, 100 amps is here, 10 amps is here. 1 is going to be like just there, pretty much nothing. All right. So to go from 2 volts to 4 volts, we're increasing it by a factor of 10. We're multiplying it by 10. Okay, yeah, all right, that seems doable. So that would mean that we're going up from 2 volts. If we go, we're going to go up to 10 milliamps. So it's going to be about there. Then for 6 volts, we're going to 100 milliamps. Well, that's there. Well, that looks linear. But then after 6, we go to 8 volts, we go to 1 amp. So each time we go up here, it's multiplying by 10. So then the next one is going to be from 100 milliamps to 1 amp. And then after 1 amp, it's 10 amps, and that's not even on our scale anymore. So we actually end up with a curve that looks like this. Sorry, it's a bit messy there. Let me see if I can do it a bit better. Oh, I can't do it better. Sorry, guys. But yeah, the idea is that it shoots off very, very, very quickly. It starts very, very low and it shoots off very quickly. I want you to compare this to this one here. As I went up, each time the current went up by 1. And so therefore, if I went from 2 to 4, if I doubled, then this would double. If I went from 4 to 8, if I doubled, then this would double. But if I compare that to here, if I go from 2 to 4, that's times 10. But if I go from 4 to 8, that's times 100. So it shoots up faster and faster and faster. That's what an exponential curve is. This is a non-ohmic device because it's not linear. That's the main reason. Non-ohmic devices are non-linear. You can see for this device that the current goes up very, very quickly, but the voltage drop doesn't. You can drop 8 or 9 volts and just, still see that current shoot up. So hold on a second, sorry. So let's grab a look at this. But maybe pardon me, sorry, I'm just figuring out what's going on here. So some non-ohmic devices form an exponential. Use this formula below to create a table of values and plot. Okay, can you guys, I'm going to pop open chat now over on the left here. Can you guys tell me, we're going to start in the middle. What's 2 to the power of 0? Check in chat. You should be able to answer things in chat now. I've enabled it. 1. 2 to the power of 0 is 1. Okay. What's 2 to the power of 1? Thank you. And 2 to the power of 2. And 2 to the power of 3. Beautiful. Sang, that was your chance. That was the first time the answer actually was 8. You missed it. All right. Can I get someone to tell me something different? Jason, take a break for a sec. Can I get someone to tell me what's 2 to the power of -1? Come on. I can't let Jason be the only one learning here. No, Jason. No. Thank you, Min. Thank you, John. 1/2. What about Aaron? What about Nate or anyone actually? What about 2 to the power of -2? What's that going to be? One over 4, correct. And then the last one, 2 to the power of -3. 0.125 or 1/8. Now, what's happening with this specific exponential graph is it's doubling. So 1 goes to 2, 2 goes to 4, and 4 goes to 8. These are all times 2s. It actually happens all the way back there. 2 8s make a quarter, 2 quarters make a half, 2 halves make a whole. So therefore, if I was to plot this on the graph, I would start with 0 being 1, 1 would be 2, 2 would be 4, and then 3 wouldn't fit on the axis anymore. If I went down, I go from 1 to a half, to a quarter, to an eighth. And so therefore my graph is going to look like this. Yeah, a little bit better. Thank you, Jason. This is an exponential. And the idea of an exponential is it increases fast and fast and faster. This is an exponential rate. This exponentials are used all the time in science, not just in maths, not just in engineering. They're used a lot. Specifically in science, we talk about a lot with biology and bacteria. One cell becomes 2 cells. Then those 2 cells can each split. When those 2 cells each split, we get 4 cells. When each of those cells splits in half, we end up with 8 cells. When each of those split in half, we end up with 16. Now, let's just say there are other examples as well. You could take, for example, let's just take a random example of like a person who's infected with a virus goes out and bumps into 2 people and passes the virus onto them. And then those 2 people go off and bump into another 2 people and passes the virus onto those 2 people. So then you end up with 4 people with the virus. And then those 4 people bump into 2 more people. And then we end up with, 8 people with the virus, and so on and so forth. This is, it's firstly, it is like mitosis. Exactly, good answer, Jason. And the virus thing is, this is why we talk about exponentials. We've been talking about exponentials a lot when it comes to coronaviruses, because coronavirus increased exponentially as each person bumped into 2 people. A person could, I think it was like, could pass, an infected person could unknowingly pass coronavirus to 2 people. And so if we're not careful, if they weren't careful, then it would spread really, really rapidly. So that's why it's important to understand exponentials. But yeah, they do play a role in when we talk about just basically these ideas. Plus, because it's an engineering maths topic, I wanted to talk about some actual maths graphing here, because you guys will end up doing exponentials later on if you end up doing year 10 intermediate or advanced. Now, what about more complex versions of these exponentials? No pencil here. This is just purely for interest's sake. Those exponentials can take different forms. If you, an exponential is designed to get larger. So this is the general form of an exponential. We were talking about 2 to the power of x. You could have 3 to the power of x. You could have 3 to the power of, 4x or whatever. But the way we talk about this is usually in this form. It's either designed to get larger or smaller the closer to infinity it gets. So you could say for this one here, instead of getting larger and larger and larger, it gets more and more and more negative. Same with the other 2. Sometimes we shoot them up going the other way. So instead it gets smaller and smaller and smaller until it eventually gets to 0. And that's kind of like how you might sort of talk about, that might be talking about how we get rid of, sorry, give me a second. Getting smaller and smaller to 0, that might be something like we talk about the value of a car. So the value of the car gets less and less and less and less until it's pretty much worthless, and that's pretty much worth 0. These other values here that I'm talking about in this section here, A reflects it. A either makes it go up or down. B is the base. It shoots out quickly. So it's going to slow increase. So it's going to be a quick increase. C moves it either left or right. So that's translating it. You guys don't need to memorize this. You don't need to know this. I'm just putting this up here because I know some of you are nerds and you might not admit it, but this might interest you. So this is a little bit of more information, exponentials. What I want you to be able to do is I would love you to be able to, this is the only part that I want you to be able to do. Take a graph, take an equation like this, create a graph, and then draw it. And all you need to do with drawing it is do these points. Notice here though that this will never get to 0. It'll get close, like 1/8 is close to 0, 1/16 is closer, but it will never actually equal 0. You actually have a name for that. You actually call it in maths, we call this line here the asymptote. The asymptote means the line that we approach but never touch. I've got some questions or maybe some more love declarations on this. Okay. So this is why I don't allow. Okay, let's keep going. Let me see, how far do I want to go today? I want to do that. I think I want to get to the end of diodes. Can I get to the end of diodes? I'm going to give it a try. So most of these exponential things are referring to one particular device, a diode. Now a diode is essentially, most people have heard of diodes because they make up LEDs. That's what the D in LED stands for, is diode. There's a lot of text here that I either want you to write down or summarize or copy later on. So I'm going to talk about these step by step, and then we're going to do 2 examples. Like I think we've got 5 examples, but they're really quick. And then what we'll do is we'll wrap up the day there. So a diode is a one-way component in the circuit. It's actually unique. One way has a little of resistance. One way only has a tiny, tiny bit of resistance. The other way has a huge amount of resistance. It's like a one-way door. If I took a resistor, what a resistor doesn't care whether a current's going this way or current's going this way. It's just going to allow things through no matter what. But a diode is more, so it's like, yeah, so a resistor is like a door like this. It's going to allow people to come through no matter what. A diode is more like this situation. So if you've got a lot of current going through, it can all squeeze through and come out. And you can go very, very easily from left to right. But if instead I was trying to go from right to left, I'm just going to keep smacking into that wall. Only a tiny little bit will make it through. That's why we refer to it as a one-way component. Ultimately, a diode only lets it to go in one way. The other way we refer to it, instead of using one way, the fancy technical term is bias or polarized, which means that it can only go in one direction. It can only go from left to right or right to left. In this case, we've got one, and we symbolize that using this symbol here. See how this picture, right? See how I did like a triangle shape? You can now see why this triangle shape exists. The current can easily go this way, but it can't go that way. So that's why it sets up in this way. The direction of the flow is the way current can flow from positive to negative. And this is another reason why we need to know the difference between conventional and electron flow. When we talk about conventional current, and when we hook up a circuit, we hook it up in this way, from positive to negative. An LED is a special kind of diode. It's just like any old diode, except the difference is that when it has a symbol that looks like this, or sometimes it's in a circle, but it doesn't matter too much. The idea is when when voltage goes through a diode, light comes off it. The last thing that's a little bit weird is a diode has a switch on voltage. So what that means is you need to have a resistor to make sure that you don't blow up the diode. The other reason as well is that if you don't put enough voltage through it, it won't conduct. You need to put a certain amount of voltage and then it will just conduct. It'll be happy. What does that look like? Well, grab a look at this diagram here. We would say that, for example, for a red diode, the switch on voltage is about here. It's about 1.6 volts. After you put about 1.6 volts into the diode, it'll switch on. It'll start to light up red. Now, if you compare that to something like, I don't know, a blue diode, you need to put more in. You need to put 2 volts in to a blue diode to get it to light up. A UV ultraviolet diode, even more. You need to put 3 volts into a UV diode before it will light up. You need to put more voltage. And again, this is current here. This is not a linear graph. The linear graph would look like this. This is not a linear graph. It starts off low and then shoots up. This is not linear. It sort of looks a little bit linear, but yeah, because it's all curvy, we would say that's not a linear device. It's not a ohmic device. So then the last little bit is to talk about current flow, and this is going to be the last section that I'm going to talk to you guys about. We'll look at what happens when you put a diode in a circuit. We're going to start off with this one, okay? Current comes out of the positive end, goes through the circuit, through the light bulb, and the light bulb lights up. Okay, beautiful. All right, that works. This one, current comes out of the battery, but notice when I go here, notice how this arrow is facing the wrong direction as the diode. That means that no current's going to go through that diode because it's facing the wrong way. When it's facing the wrong way, it's pretty much like an open switch. So therefore, this is off. Whereas this one here is very clearly on. On only has one end. Don't ask what's happened. It's been a long day, ladies and gents. Let's grab a look at this example here. In this one, the current comes out of the positive. It goes through this diode because it's facing the right way. Goes through the light bulb. But then when it gets down here, it's facing the wrong way. So therefore, it's not going to conduct electricity. Therefore, this light bulb is going to be off. So it needs to be able to go through all of the diodes in order for it to be on. Even though the current goes through the light bulb, it doesn't complete the circuit. Because the current can't complete the circuit, it doesn't light up. I want you guys to tell me, with this example on the left, right, which one is on and which one is off? Or are they both on? Or are they both off? Write it down in chat or say it out loud. Up to you. John says A. Aaron says A. Jason says both off. John says it's on, but didn't actually tell us which one is on. Which one's going to be on, A or B? John? Okay, can I get someone else to guess? Marco, Vincent, someone. Is A on or is B on? A is on. Thank you, Emre. Reese says A is on. All right, let's go have a look. Let's see what happens in this example here. We've got current coming out of the top. It gets to this point, and it can either go down or it can go across. In this one, the arrow matches the same direction as the diode, so the current goes through, and it can keep going back to the battery. It will always go back to the battery, leaving this one to be on. This one, though, doesn't match. Because it doesn't match, it doesn't go through. It's like an open circuit. So there, oh, sorry, Aaron, therefore it is off. Okay, what about in this example? B is off. Yep, let's go through this example here. This is the last example of the day. This is designed to be a bit of a challenge. Well, yeah, I want you to tell me, is A on, is B on, is B off, is A off? What is going off? B is on? What about A? Is A on? A is off. A is not on. Let's grab a look at this bad boy here then. Only B. Rush B. We're not rushing B. If we go across here, we can split. One goes this way and one goes up here. Now the one that goes across to the right will go through, but this one is not matching the direction. So therefore, as it will then light up B, and then I can split. I can either go to the right or I can go up. If I go to the right, then I can't conduct. If I go up, now when I got to this point here, you could stop and you could say to yourself, is it going to go left or is it going to go right? Okay. It is not going to go left. The reason it's not going to go left is because if it goes left, it's moving away from the battery. Current always moves towards the battery. So because the current is moving towards the battery, it is going to go to the right. It can conduct through this, so it's going to go this way. And then going to get back to the circuit, meaning that B is on. This is often a common mistake here. Well, it's not a common mistake. I'm going to let you guys know. About 4 years ago, the first time I taught this, I actually taught it completely wrong. I said A would be on. I said, oh, the current's going to go through here and it's going to wrap around. And I'm like, no, that's not how it works. Current, electrons never would go away from the battery. You've got to wait. At this point here, they could go towards the battery or away. It's not going to go, it's always going to go towards the battery. Now, it's a bit different in a circuit like here, because both of these paths go towards the battery. So it doesn't matter if it goes down here or to the right and then down. But here, this path is to the left, is going away from battery. So that's it. And that's all I wanted to talk to you guys about today. That's all the information about, that's a lot of stuff that I've talked to you guys about. I spoke to you guys about ammeters, voltmeters. We spoke about ammeters. We spoke about voltmeters. We spoke about exponential. We spoke about ohmic versus non-ohmic. Graphs. We then talked about exponentials. And then we even talked about diodes and diode circuits. Look at that. That's a lot of information here. So if you missed out on something here, you may need to re-watch this video, go back to something that you missed and like re-go over it. We're going to slow down a little bit tomorrow because tomorrow we've got a single period. So we're just going to do a little bit of stuff. I might get you guys to work on some questions, but yeah, just to practice all of this stuff that we've been doing, but ultimately we're going to slow down a little bit, and then probably Thursday we might start to look at, probably on Thursday we might start to look at power and circuits.